So today we're going to be talking about the method of characteristics, and this method is applicable to first order linear PDEs, and what that means is we'll be looking at equations of the form A, xy, ux plus b, xy uy plus c, xyu plus d, oh, my bad, that's an equal sign, equals dxy. Now what this means is we have an equation and then we have a partial derivative of u with respect to x and a partial derivative of u with respect to y. In addition to equations of this form, we must have that a, b, c, and d are in the class of continuous functions that map R2 to R1. So all that really means is that these are all continuous functions and they all take two values, x and y, and then output one value, okay? Nothing too crazy. And also we have an initial condition that usually takes this form. So whenever our y value is 0, we end up with an output for u that is just a function of x, okay? So this is the situation we're looking at. A first order linear PDE, these are the coefficient functions, and this is our initial condition. Now what we want to do is we want to make this equation something we're familiar with so we can solve it using methods we learned in ordinary differential equations. Now, let's see how we do that. So, and can you guys see this marker? It's fine? Okay, cool. Okay, so step one, what we want to do is take our AXY, UX, and our BXY, UY, and what we're going to do is we're going to re-parameterize what variable we're looking at. And by doing that, we can create a system of ODEs. So I'll show you what that means. Basically, what we're going to do is say, let me change markers. That's much better. So the derivative of x with respect to s equals this part, which is just AXY, and our derivative of y with respect to s equals BXY. So now we have a system of ODEs, and all we did, we just took those partial derivatives and parameterized them with respect to s. Now, why we do this is because the solution to these, which ends up being x as a function of s and y as a function of s, these are called the characteristics of this PDE. And when we're only concerned about our solution, u, to this PDE on the characteristic surface or curves, then we end up with an ODE, which is just v of s equals u x of s y of s, okay? And now we have something we can solve. All right? So that's step one. Step two, you want to solve for x and y using the methods we learned in ODEs. So you're going to take these, which are just separable equations, you solve, and you end up getting the derivative of v with respect to s equals the partial derivative of u with respect to x, and then the derivative of x with respect to s, plus the partial derivative of u with respect to y, times the derivative of y with respect to s, and that just ends up being our function a we had earlier of s partial u plus b of s partial u, okay? So this is what we end up with. Then in step 3, what we're going to do is replace what we have here from our original equation with what we just found, which is our derivative of v with respect to s. And once we replace that, we end up with a first order linear ODE we know how to solve. Okay, so replace, and then step 4, we're going to solve, and then last step 5, we just want to put everything back in terms of x and y. So put back in x and y. Okay, so right now it seems pretty abstract, so we're going to look at an example of how to do this, okay? So I'll start the example here. If I need more space, I can erase some of this. So the example we're going to be looking at is the partial derivative of u with respect to x plus 9 times the partial derivative of the partial derivative of u with respect to y equals 0. And our initial condition is u x0 equals sine of x. All right, so is it of the correct form? It is. And we have our initial condition. Everything's good to go. So step 1, we are going to take our axy and bxy with our partials. So this has an invisible 1 coefficient, so that means that axy equals 1, and our bxy is this 9. Okay, so we have axy equals 1 and bxy equals 9. Now, if we remember from here, all we're going to do is the derivative of x with respect to s equals axy, which is just 1. So we have dx ds equals 1, and dy ds equals 9, okay? So step 1 is all done. We have a system of ordinary differential equations. Now let's look at step 2. All right, in step 2, what we want to do is we want to parameterize, well, actually, what we want to do, my bad, I misspoke, is solve for x and y, since we've already parameterized with respect to s, okay? And how we're going to solve? Like we would solve any separable equation, okay? So we're going to integrate one ds, these cancel, and then we just end up with x equals s, since we're integrating with respect to s plus some constant, we'll call that c1 for now. Now we're going to do the same thing with this other ODE we just found. So we end up with dy ds equals 9 ds, okay? Cross these out. Y equals 9s plus some constant. We'll call that C2. All right, now here we want to take our initial condition into account. To make our lives easier, we want to have y be only dependent on s. So then if s is 0, our entire y is 0. And then that just makes things easier for our life. So we'll just make y equal to 9s, and then x equals s plus some constant. For now, we're just going to call this constant alpha. All right, so now we have our equations. X equals s plus alpha, y equals 9s. All right, now we'll go to our next step, which is where we rewrite things. So I'm gonna erase this first part up here. Okay, I guess erase it as much as I can. So we have our equations. I'll just rewrite them over here. X equals S plus alpha. Y equals 9S. Did I rewrite that correctly? It did, okay. So now we're gonna move on to our step 3. And that's just rewriting the equation with respect to our new variable. And what that is u, the partial of u with respect to x, plus 9, the partial of u with respect to y, just equals the derivative of v with respect to s, which equals 0. And in our previous steps, we found that these end up being this because we solved for those, okay? And in our next step, 4, this part that we ended up getting when we replace things, we know how to solve. Again, it's just a separable equation. So we're going to dv over ds equals 0, ds. This cancels, we end up with v equals some constant value. Let's call it C3 for now. And this C3 ends up being v of 0, which equals to, from our initial condition we saw over here, sine of x, which is just sine of alpha. And the reason it's sine of alpha is because when s equals 0, y equals 0, and x equals alpha, okay? So that's how we got that sine of alpha. And now what we're going to do is, for our last step, put everything back into terms of x and y. Okay, so when I put everything back in terms of x and y, I like to start with my y because it only has one variable. So, step 5, y equals 9s. So we're just going to divide over that 9 to get s. We end up with 1/9 y equals s. All right, and we have x equals s plus alpha. Since we know s, we're going to replace that with 1/9 y. X equals 1/9 y plus alpha. And we're going to subtract this over to get alpha alone. So we have x minus 1/9 y equals alpha. All right, so we have what s equals, we have what alpha equals, and now we're just going to put that into our equation. So we end up with u equals sine of, since over there we got v0 equals sine of alpha, we're just going to take our alpha value and put that in, x minus 1/9 y. All right, and that is the solution when we're only concerned with the characteristic surface. So I'll show you what that means in a second with the next example. All right, so the next example we'll look at is, well, before I move on, are there questions about this example? No? All right, cool. So the next example we'll look at is 7, the partial derivative of u with respect to x, plus 3, the partial derivative of u with respect to y, plus x u equals 0. All right, and our initial condition is that when y is 0, the solution is just x. All right, so we have the proper form and we have our initial condition. We can keep going. So back to step 1. We're going to take our axy, which is just this coefficient right here, equals 7. And then we have our bxy, which is just this coefficient right here, equals 3. And we're going to create a system of ODEs from those. So we end up with the derivative of x with respect to s equals 7. And again, that's when we parameterize this by s. And the derivative of y with respect to s equals 3. All right, step 1 is complete. We have our system. Next, we're going to solve for x and y. Step 2. And since these again are just regular separable equations, we know how to solve them. So we do dx ds equals 7 ds. These cancel, so we just end up with x equals 7s plus some constant. We'll call that c1 for now. And the derivative of y with respect to s, ds, equals 3 ds. These cancel, so we end up with y equals, let me make sure I have that correct. Yep, y equals 3s plus some constant c2. And again, because our initial condition has y equaling 0, to make our lives easier, we just want y to be solely dependent on s. So we end up with y equals 3s, and we'll call this constant for now alpha to make our lives easier. X equals 7s plus alpha. All right, so now we have what y equals parameterized by s, and we have what x equals parameterized by s and alpha. So we can move on to our next step. Step 3, which is where we start replacing things. Okay, so we know that the derivative of v with respect to s equals these things we found. However, what we also need to take into consideration is, let me see, am I at the right part? Okay, yeah, equals equals the 7ux plus 3uy, and we need to take into account here. The last example we looked at didn't have a term like this, so we just need to reconfigure that with respect to s. So c xy equals x, and we know x equals 7s plus alpha. And now we can replace things from our equation up there. So we end up with db ds plus 7s plus alpha. And instead of having a u, we're just going to replace it with a v. V equals 0. Okay, now we have something we know how to solve. This requires an integrating factor, and we'll look at that in the next step. Step 4. So in order to solve our equation, like I said, we need an integrating factor. So mu of x equals exponential of this. So, exponential of the integral of this, 7s plus alpha ds. All right. And that just ends up being 7s ds plus alpha ds exponential of, And then 7s is just 7 times the integral of s, which we know is s squared over 2. So, I don't know why I rewrote that. Which is just 7 over 2 s squared. And then alpha s is just alpha times the integral of 1 ds, which is just s, plus alpha s. Okay. So this is our integrating factor, so we're going to have to multiply it out to all the terms in our equation. So that's e raised to the 7 over 2 over 2 s squared plus alpha s times dv ds plus e 7 over 2 s squared plus alpha s times this. So times 7s plus alpha v equals, and then 0 times our integrating factor is just going to give you 0. All right, and this is a product rule. So e 7 over 2 s squared plus alpha s v prime equals 0. Once we integrate, we get that e to the 7 over 2 s squared plus alpha s v equals some constant. We'll call that C3 for now. And like the previous example, this constant, oh wait, my bad. I'm getting ahead of myself. We need to get v alone and have it isolated. So we're just going to divide by this value. We end up with v equals C3e raised to the negative 7 over 2 s squared plus alpha s. All right, and this we end up finding this C3 equals to alpha because C3 equals v sub 0, because if we put 0 for s, this just ends up being 1. So v naught, which equals alpha. So now we know that v equals alpha times e to the negative 7 over 2 s squared plus alpha s. Okay, so we have that. We did a lot to get here, but there's one last step. What we want to do is just get things back in terms of x and y. So I'll go back over here. I'll erase everything but the original equation, just so you could see where we started and now where we're going back to. So v equals alpha e raised to the negative 7 over 2 s squared plus alpha s. And again, I like to start out with what y equals because it's only dependent on s. So we know that y equals 3s. So then we divide out that 3. We end up with 1/3 y equals s. X equals 7s plus alpha. We're going to replace that s with what we found s equals in terms of y. So that just ends up being x equals 7 times 1/3 y plus alpha. So x equals 7/3 y plus alpha. And then we subtract that 7/3 y to the other side. So x minus 7/3 y equals alpha. All right, so we have our alpha value. We can put that there. So v equals x minus 7/3 y times e raised to something. So I'm gonna handle that on the side, then fill it in here, so we're not doing all that work. We had in our exponent 7/2 s squared plus alpha s. So negative 7/2 s squared plus alpha s equals negative 7/2 times, oh wait, my bad, times, we know that s equals to 1/3 y, so 1/3 y, that gets squared, plus alpha, which is just x minus 7/3 y times 1/3 y. Okay, and to not bore everyone with all the calculations, that ends up being 7/18 y squared minus 1/3 xy, and that is our exponent value. So 7/18 y squared minus 1/3 xy, and that is our u. Okay, and in order to understand where this solution lives, let me pull up the curve I was talking about. Oh. Yeah, it's your account. Oh, it's locked out. Which button do I press?
The on?
On, oh,
Mhm.
thank you. Okay, can you all see the curve fine? Alright, so this surface is basically where our solution lives. So if you're worried about something that's all the way out here, this method is not gonna work. Or it's not gonna be accurate to where you're looking toward. So this is for example 2, it's applicable, and this ends up being our solution to the equation. So I just want to show that to show, although this method is very useful, it's not applicable to anything and everything. It can be limiting. So yeah, if you just took ODEs and you're like, I love differential equations, and you move on to PDEs, this will be probably the first thing you learn. And that's it.